Okay, thank you for this opportunity. Hello, everyone again. My name is Dmytro. These slides are available online. You can see the URL at the bottom of the screen, and I will repeat it again at the end if you want to check out the slides right away. But as Tina introduced me, I work in Lund University together with Ulrika, and this is one of the papers that we've written together, and this is a short presentation that I will also present next week at the CETEC meeting. So, talking a little bit about encoding and updating uncertain judgments. Basically, I want to start by kind of reflecting a little bit on the procedure, how we fit the distribution. The standard practice is that we elicit some sort of quantities, quantiles most likely, and fit a known distribution, something that we are familiar with. As one of my friends says, that the distributions that we fit to the elicited quantiles are not necessarily designed for describing knowledge. They're designed for describing data. So like reflect on this CDF question, for example, is that you're saying, so how many values, or what's the share of values that would be below this certain value? So you start with X and you go towards probability. In the knowledge domain, you would probably start with a probability. You start, okay, I know median, right? I'm interested in median, and you would go inverse question. So what the value would correspond to a median? And that's one of the questions that may be interesting to reflect on, but most of the distributions are designed for describing samples, not for describing knowledge. So there are some implications of that. Other thing that I wanted to talk is that there are basically two schools of thoughts regarding judgment. Those quantiles that we're listening from the experts, they are either very noisy and unreliable, or they are super precious and untouchable. But like of course I'm exaggerating here, but for example, Levy and Ramsey, to a certain extent, talked a little about inconsistent belief. Both of them believe that the rational human being, of course, needs to have consistent belief, but it's possible to hold inconsistent belief for relatively long time because we don't know what we know. It's the knowledge is there, but it's inaccessible, or it's basically biased by our imperfect rational thinking. Therefore, when we're eliciting, we're somehow sampling from those beliefs, and they may be inconsistent. Or as Definetti would say, if your belief is inconsistent, then it's possible to take advantage of you. And therefore, we should correct those inconsistent beliefs and fit to the rational and coherent set of beliefs, which would be quantile probability pairs, for example. So this sampling versus fitting is the two paradigms that are also appearing in the literature, and there are some links where, for example, Mr. Hartman and the peers in Finland have designed a procedure for sampling from experts' belief, and we're working with fitting to the elicited quantile probability pairs. Okay, well, I also want to kind of reflect a little bit on this hairball. I called it hairball because this is a perfect, very interesting chart describing known distributions and relationship between them. And also link is there, references here. It's very confusing at times, difficult to know which distribution to pick and to fit to elicited quantiles, for example. So we go with familiar. We know maybe a few of them. Some distributions are very closely related, so it doesn't matter which one of them you pick. And those familiar and convenient, therefore convenient distributions are not necessarily always suitable. So there is some kind of degree of arbitrary judgment that is made on behalf of the modeler, which distribution to pick. The last point here is that some parameters are truly mean. Not only that they're mean values, but they're also evil in the sense that they are counterintuitive, maybe non-independent. They may be difficult to elicit, difficult to ration about, and therefore, when we're asking experts to give us estimates of those parameters, we're actually asking a little bit too much of the experts. They cannot wrap their head around it, and therefore, garbage in, garbage out is a really reasonable risk to consider. All right, so we more or less settled around that question that fitting to CDF is hard, but fitting densities is harder. So let's say if you have elicited these bins in a procedure that looks like histogram, then might be more difficult to fit a smooth line through them. CDF is a little bit more reasonable or easier to reason about. So ideally, if you would elicit these points, you would want to put some sort of smooth curves through those few quantile probability pairs, because it's very unlikely that the judgment is kind of piecewise. Most likely it's somehow smooth going through those pairs. And the problem is that there's infinite number of ways of doing it. It's not that easy to pick which curve to put through them. And also we need somehow closed form CDF from it, and inverse for sampling. And there is always a problem of tails and boundedness, because it's more difficult for experts to reason about the tails, but it's more critical to elicit them precisely or as close as possible. So have a look a little bit closer. Today we're going to talk about these distributions that are parametrized by quantile probability pairs. And there's a small chart I'm going to make bigger to look a little bit closer at those distributions, 3 of them here. So first I want to talk about this Meyerson distribution. Meyerson distribution is by Roger Meyerson, the Nobel laureate. It's unbounded, and this blue line goes from minus infinity to positive infinity, but here it's reasonably kind of, on small probability below 0. And the data here is, it's actually elicited quantiles are from the database by EFSA for chronic consumption of bitter chocolate. And this is elderly category from 2010. So these points are coming from the database. They have been elicited by experts. And here we're looking at the 5th quantile, the 50th quantile, and the 95th quantile, it looks. So my Meyerson distribution goes through these 3 points, and it is parameterized by those 3 points. There's nothing else that Meyerson needs. 3 quantile probability pairs, and I got my distribution in this smooth curve here. Another example is this Johnson quantile parametrized distribution. It's semi-bounded. It's made by folks in Texas. And it is starting from 0, and it goes through the same 3 points. But as you can see, because it's bounded, it's going slightly, different curve, following slightly different path. Maybe not that much in the upper tail, but the lower tail is bounded, and there's some differences here. And then the third distribution that I'm going to talk today about is metalog. Metalog can be bounded or semi-bounded. And in this case, it starts from 0, and I fitted it to a different quantile. Actually, these 4 points, or even 5 points, were elicited in the database. So you could find an estimate of a 5th to 10th, 50th, 95th, and 97.5 quantile. And I fitted through 4 points. So this metalog is 4-term metalog, fitting through the 4 points here. And you could argue that the judgment here between the 5th and 10th quantile is probably inconsistent. It's very unlikely that it's such a steep rise here, but maybe. So just following through these points, again, these 4 points completely define metalog distribution, and it will be parameterized by it. And then I have CDF at every point. So that's the kind of distributions that we're going to talk about today. So how are they made? How are these distributions made? There are basically 2 main groups of distributions and 2 ways of making them. One is through reparametrization, and Meyerson distribution in particular is made like that, and Johnson QPD is made like that. And you basically fix the probabilities. You specify these are the probabilities that I want to elicit quantiles for, and then the elicited values would go corresponding to those specified p-values. And in a non-SPT world, and non-SPT, I mean, the probabilities are not symmetrical or may not be symmetrical. Metalog and simple Q-normal distributions are there. And it's made by implicit functions. What we mean by implicit functions is that you basically have, so for 4-term metalog, you have 4 individual quantile functions, individual equations, and a sum, or basically a system of those 4 equations would give you a distribution. And that's how you find the parameter values, is through solving the system of 4 or 3 or 4 equations or more equations. For metalog is extensible. And that is the method that Tom Keelan has proposed in his paper. And I'm using that distribution here as well. So as you can see, it's not easy to draw a line, but on the other hand, it's possible to draw a smooth line. So for experienced analysts, there are some distributions to choose from, and you can have a situation where you follow the elicited values exactly. These 3 points will be always, or 3 or 4 points will be always honored by the distribution because they represent the parameters of it. I can stop and ask for questions if there are some like immediate questions you want to shoot. Just yell, please. Or you can put question in the chat and then we'll address it later. All right. So moving on. So let's say that we accept one of these distributions as a model for data, for describing data. In order to learn, in order to update our beliefs about the quantiles, we need to admit some sort of uncertainty into these parameters, either to quantile values or probabilities or both. They need to be allowed to vary. Another important condition is that the new draw or new set of these quantile probability pairs need to remain a valid QPT, or this quantile probability tuple as we're talking about it in the paper. So there should be no overlaps. For example, a higher value on the quantile, higher quantile value need to correspond to necessarily higher cumulative probability. You don't want to end up in a situation where they clash into each other, these points clash into each other by sampling. So it kind of makes a little bit the sampling from the distribution a little bit more tricky. Here is an example of yeah, so before I go to the example, here's an example that we're going to look at. Another important kind of concern when specifying that model, the model with quantile probability pairs, is that there should be some sort of covariance matrix specifying how individual QP pairs are dependent on each other, either through covariance matrix or by nature of distribution itself. And we'll come back to that in a second. And as I already mentioned, the monotonicity constraint is such that the sampled quantile probability pairs need to still represent a valid, tuple, and therefore we could look at the intervals as categories. So here's in my example, look at these 3 points that were elicited: 4 grams of chocolate corresponding to roughly 25th quantile, 8 grams roughly to 50th quantile. It's actually higher, but around that. And the 16-gram consumption per day is corresponding to a little bit over the 75th quantile. So you could look at those as categories. So people who consume only up to 4 grams a day, they are morning coffee consumers. And 4 grams is corresponding to 1 bit of chocolate, roughly. I measured it. It's 4.2 grams, I think, 1 bit, at least on the chocolate that I eat. And the after dinner, I call them, these are playful categories that I assign. People who consume up to 2 pieces, up to 8 grams, basically, I would call them after dinner consumers. And then there are some other consumers that consume up to 4 bits, and that would be every meal. And then there's this kind of unlimited category of sweet tooth consumers that would consume above 16 grams of chocolate every day. And the limit is, sky's the limit, basically. So you could look at on the x-axis, these categories would add up to 1. So look at this. The width of the first category is kind of adding up to a 1 where all categories are included. And whenever you have something adding up to 1, you would hear this or see this writing on the wall, Dirichlet, because this is a situation of multinomial distribution for which the prior is Dirichlet. And so you could reason about it. So now let's accept that it's the probabilities that are uncertain. In my quantile probability pairs, it's the P that is uncertain and Q is fixed. So for example, my morning coffee consumers, for the sample of 100 consumers, 24 of them would be in the morning coffee category. And then we can elicit experts' uncertainty around this picture by asking him to move around assign more people to the morning coffee consumers or less people to morning coffee consumers, essentially reframing the question of eliciting uncertainty in probability into uncertainty in relative frequency. And that's much easier to reason about. So here's my morning coffee consumers corresponding to the first bin visualized on the side. All right, so as I spoke about, Dirichlet, or the generalization of it is called Connor-Mosiman distribution, is the prior for these probability bands, uncertain bands, They're corresponding to a fixed vector of quantiles Q star, and that together we call Q Dirichlet prior. So it's a Dirichlet distribution assigned to 4, 8, and 16, the 3 Q star values that are going to represent the quantiles for which the uncertain probabilities correspond to. Yeah, and so the way you would conduct an interview is something like this. It's a bit of longer text, but can you imagine that you're sitting in the room and I'm asking you this question. Consider a sample of bitter chocolate consumers, say 100 people. According to your assessment, there should be only 24 people that consume up to 1 bit of chocolate a day. We will interpret this assessment as you believing that there's about equal chance that the actual number of morning coffee consumers in the sample will be above or below 24. I will interpret this as a median assessment. Would you like to reconsider this value? This is a kind of poking around the number of consumers that, like in this hypothetical sample of 100 consumers of bitter chocolate, and kind of testing around the median value. And then the elicitation can continue like that. And actually, Alfadelli and Gattuate has designed a way of eliciting Dirichlet distribution, which is built up on this sort of questions. And it's eliciting Dirichlet distribution by a sequence of conditional beta distributions fitted to quartiles. So we would elicit a quartile around this median, and the bottom 25th and the upper 25th. 25th, 75th quantile around the 24 people here. So conditional SPTs, and by SPT, I mean symmetrical probability triplets. This is another abbreviation here, sorry. So they're conditional because each new category is building on the previous assessment. And last band is assessed as 1 minus P. So we would say, what's the total number of sweet tooth consumers considering the basically upper tail or complementary probability. And then the beta distribution is fitted to each of the triplets. I mean, you can argue that the points are honored exactly only in the kind of predictive assessment in this curve, the black curve, but the individual curves will follow the beta distributions, which are not maybe perfectly fitted, but the procedure that these folks describe is fairly well done, accurate, pretty accurate. And then we can assemble these into a vector, parameter vector for Dirichlet or Connor-Mosema distribution. And so here's, for example, the elicited data. My morning coffee consumers were elicited to be 24 in the median, and then it's varying between 18 and 30. So imagine the width of this first category can be as high or as big as 30% or as low as 18. So my 4 gram can correspond to 18th quantile or the 30th quantile. And after dinner is the second category is varying between 25 and 36 with a median of 31. And then the sweet tooth category is the complementary, the upper bound. So as you see, I'm left out the category 3, which is now implied as a rest of the distribution. And that is varying between 8 and 20. This way, these values are enough to combine them or roll them back into a Dirichlet distribution. And the resulting distribution that we get is a 2D distribution because it characterizes the uncertainty in the quantiles of the hypothetical sample. And then we can talk about aleatory uncertainty, which is kind of variation in sight, and the uncertainty in the parameters that are defining our distribution. Note that one kind of restrictive feature of this is that we did not elicit any covariance matrix because the correlated structure is already implied by the distribution itself. The Dirichlet distribution has perfect negative correlation between the categories. So increase in one category necessarily means decrease in other categories. And therefore, my distribution would move basically every time the upper quantile would go up, the lower quantile would go down, and vice versa. And that is a restriction, but let's say in Connor-Mosema distribution, which is another way of wrapping these data into, the correlation can be relaxed, and there's more way of defining flexible dependent structure, judging from the expert, basically, the values are given from the expert. This paper is very applicable. The only difference that we've made is that we've defined this slightly kind of specifically related to these categories, which are pinned basically to fixed quantile values. So yeah, the elicitation happens on conditional on the median value of the previous category. So what you can do with this? What can you do with this Q-Dirichlet distribution? You can sample from it. So this is how the prior predictive spaghetti would look like. These are samples from the Q-Dirichlet distribution and then fitted metalog to them. And there's a lot of uncertainty in this, in the upper tail, quite a lot. And the density function looks pretty ugly. Hairball of distributions. This is, I think, 1,000 samples here. So before updating, this is where our initial beliefs look like. So this table translates into this hairball. What does it mean for the extreme consumers, or let's say the median consumer, the extremely high consumer of chocolate, and the low consumer? These are the, I define the 5th and the 95th quantile as the high, median, and low consumer, and these are the uncertainties in the consumption of this low consumer, median consumer, and high consumer. So you can see that for low consumer, it's between 0 and 4 grams, as we've kind of elicited to make sense, almost uniform distribution here. Median consumer is centered around 8, and the high consumer is, yeah, pretty high. So what can you do then? Well, we can, as we discussed already, these quantile values, Q star, will define the location of our distribution, and then the elicited uncertainty will define its shape, these p-values or Dirichlet that describes variance in the p-values. So this is a specification of the model. I'm going to kind of walk through it slowly. First is that we're sampling from the Dirichlet distribution with this alpha parameter vector, which kind of is the result of that table. And then we get a simplex of size n+1. This is a simplex. Delta is a simplex here, right? It's parameterized by the Q star, that vector of quantile values, and the alpha, which is table wrapped into a vector. So simplex of size n+1. Then we can accumulate that simplex of size n+1 to get back into the cumulative probabilities, because we're not interested in the simplex. We're not interested in the, I'm going to go back quickly to this table. We're not interested in the categories. We're actually interested in the quantile values. For that, we need to roll them up, right? Do a cumulative sum on them. And that's the second operation here, is cumulative sum of the Dirichlet sampled simplex, and that will give us cumulative probabilities. And those cumulative probabilities will be used in the likelihood. The metalog distribution is a quantile distribution. I'm going to talk about quantile distributions in a second, but we'll need intermediate U values. These are the depths or the probabilities that correspond, the CDF probabilities that correspond to an observation. We take a data, X here is data, and then parameters are P and Q star, and we numerically estimate CDF because metalog is not invertible. And then the density quantile function is a replacement for PDF for distributions that lack PDF, will give us the likelihood. It's an indirect likelihood. Since metalog is a quantile distribution, we use for the likelihood, we use the density quantile function, which is reciprocal to quantile density and numerically equivalent to PDF. So we started with just elicitation and end up with quantile parameterized likelihood. Hopefully, this kind of gives you a progression of our thought as well, how we kind of arrived at that solution. There's more to be read in the paper that we've published last year on the indirect inference, and I'm going to walk you quickly through it. So what's the reasoning kind of behind that Bayesian updating? This looks a little bit unfamiliar. F of Q of, so we're going to talk a little bit about that quickly. So Bayesian updating can be restated in terms of quantile functions and their densities. Quantile functions are inverses of CDF. So this is distribution function, and inverse, imagine the Möbius loop. Inverse of it, on the other side of it, there is a quantile function. The derivative of the CDF is probability density function. You can similarly take a derivative of the quantile function and get to quantile density function. So it's just a derivative of quantile function with respect to U, right? And then quantile density function, reciprocal of it, would be numerically equivalent to probability density function. So this ratio here, which is 1 divided by Q, small q of U, is called density quantile function. And if you don't have a PDF, which is the case with metalog, this works just fine. So if you can make a derivative of a quantile function, you're pretty much all set to calculate the likelihood. And that is what the math here implies, that for a random sample of y underscore, this is a sample of size n, we can compute these quantile values, q underscore, which is quantile function of probabilities u1 through n, such that each probability is a CDF, corresponding CDF, given the parameters. We'll call them depths. And then, so starting from, this is a standard Bayesian formulation likelihood. The f of theta is a prior, and then updated would be f of theta given y. The likelihood here can be restated, or the whole basic equation can be restated in terms of these underscore q instead of underscore y, because they're equivalent. It's the same thing. And where indirect likelihood would be, instead of product of densities, you get product of these densities of quantiles, which is the density quantile function which I described, and the depths are here. So there's one intermediate step that is required, which is finding these depths, intermediate CDF values corresponding to observations, and that where is numerical approximation is required. So as long as you have a software that can do MCMC sampling and a root finder to invert the quantile function, you're all set, and you can have a Bayesian inference using a distribution that doesn't have a CDF or PDF. So after updating, how does it look? Well, this is posterior predictive spaghetti. This is the data. That's the data we had. And because our priors were heavily skewed to the left, basically we believe that the consumption is actually smaller. The data has shifted quite a lot, and we have a lot less hairball here in the posterior. And there's still some uncertainty remains, but that's the updated distribution. We have much clearer picture on the lower, median, and high consumer. High consumer is now centered around something like 60 maybe. Median consumer is about 12 instead of 16, and the low consumer is 2.5 roughly. So wrapping up, and this is my last slide. Asking experts to provide uncertainty about the elicited quantile probability pairs or quantile probability tuple is enough to quantify uncertainty about the food consumption. So we elicit the QPT, we elicit the 3 values or 4 values, as many as you need, and then we ask about uncertainty around those values, and that is enough to basically specify the model and be able to update it. This approach is specifically useful when data is sparse, where most of the knowledge comes from the experts, and we rely on the judgment rather than a lot of data. Hybrid elicitation, this procedure that I walk you through, like predictive, describes only observable quantities. So in whole process, I didn't talk about the abstract parameters. There was not a single parameter other than something that's related to what the expert knows. It's only observable quantities that we're discussing. At the same time, like parametric elicitation, we'll end up with characterization of uncertainty in the model, and therefore we're able to update that belief. So hybrid elicitation is sort of observation level parametric elicitation for the models that are parameterized by quantiles. And this Q-Dirichlet distribution that is prior for this model is a 2D distribution that separates aleatory and epistemic uncertainty. And we're still working on the paper to kind of talk a little bit more about it. But if you want to learn more about the method, there's a preprint published on OSF, and there's very good paper by, again, Finnish colleagues, Mikala et al., which discuss different ways of eliciting priors. I think that's the end of it, and there's lots of references, and if there are questions, I'm very happy to answer them, and the URL is for you here.